Hello, I'm Kirk Weiler, and this is Common Core Algebra 2 by eMath Instruction. Today, we're going to be working on Unit number 10, Lesson number 3, Creating Polynomial Equations. So in the last lesson, we investigated how the graphs of polynomials, if I can talk correctly, relate to the zeros of the polynomials and to their long-run behavior. We also looked at how we could use the zeros of a polynomial to help factor a polynomial expression. Today, we're going to be building or creating the equations of polynomials in their standard form by knowing what the zeros of the polynomials are. So let's jump right into this and understand how it works. So the factored form of a polynomial. If we know the roots or the zeros or the x-intercepts, here I'm going to call them roots, root 1, root 2, root 3, root 4, etc., of a polynomial, then we can write it in its factored form like this. Now, there's one little piece in here where a is some number, okay, and it's some number that must be determined. In fact, it's the leading coefficient of the polynomial, the leading coefficient, the coefficient on the highest powered terms. You know, you could also say it's some kind of numerical GCF that gets factored out. Now remember, this factored form of a polynomial really comes from the zero product law, this idea that if we're solving a polynomial and we've got it factored, what we're really doing is we're finding its x-intercepts, we're finding its roots, where it goes into the x-axis. All right. And what we're going to be doing is we're going to be seeing how we can use this factored form of a polynomial to then create the standard form. And remember, standard form is when we have things that looked more like this: ax to the n plus a n minus 1, x to the n minus 1 plus a n minus 2, x n minus 2 plus. This is the standard form, right? This is the factored form, all right? So let's see how this all kind of plays out really quickly. I'm going to delete that, keep that factored form up, and let's start with a quadratic. Exercise 1 says, determine the equation of a quadratic function whose roots are -3 and 4, and which passes through the point 2, -50. Express your answer in standard form. Verify your answer by creating a sketch of the function on the axes below. All right, well, here's how this works. All right, I don't know what the value of a is, but I'll figure that out eventually. What I do know is in order to have a root or a zero or an x-intercept of -3, I would have to have a factor of x plus 3. In order to have a root or 0 or x-intercept of 4, I would have to have a factor of x minus 4. So this is the factored form of that. Now what I don't know yet is the value of a. Now I could multiply all of this out first and then find the value of a. But I've always found for myself and my students that it's easiest right now to find that value of a. All right? Now, the way I'm going to do that is by using this extra point that I was given, this thing right here. That will allow me to find a. And I'll find it the way that we often do this. I'm going to put in -50 for y, and I'm going to put in 2 for x. You see, if that point lies on the curve, then this must be a true expression. Well, what does that give me when I work on it? Remember, all of this is multiplication, so I get a 5 there, and I get a -2 there, so I get -50 equals -10 times a, which of course then means that a is equal to 5. So in the factored form, let me change back to blue, in the factored form, we have a equals 5 times x plus 3 times x minus 4. So this is truly the factored form of this quadratic. Factored form. It is not, however, the standard form. The standard form means that it's all been multiplied out and that it's been written as a sum of power functions. So this is where you have to do a little bit of extra algebra, and it's a little bit annoying, but I think I would multiply these out first. Many of you can probably do that in your head. You get x squared minus x minus 12. Okay, if you FOIL it out. Then if you distribute the 5, finally, you have y equals 5x squared minus 5x minus 60. And that is the standard form of that quadratic. Now, what's really cool is that we can definitely verify this on or using our graphing calculator. So let's do that. Let's pull out the TI-84 Plus right now. All right. And what I'm going to do is I'm going to go into y equals. I'm going to clear out anything that's there. All right. And I'm going to put in that quadratic. So in y1, I'm going to put in 5x squared minus 5x minus 60. All right. Pause for a second. You check yours. I'll check mine. Make sure that it looks good. All right. Now what I'm going to do is I'm going to go in and I'm going to set my window up according to what's on that grid or what's on those axes. So let's go into the window. For x minimum, let's put in -7. For x maximum, let's put in +7. For y minimum, we're going to put in -100. It's a little bit bigger than what we're used to. And for y maximum, +100. Great. All right, make sure your window's correct. -7 to 7 in x, -100 to 100 in y. And now let's hit the graph button. All right, and what we see is we do in fact see it crossing the x-axis at -2 and at +4, and we get a parabola that looks, that didn't look very nice. Something like that. Now the only question is that extra point, that 2, -50. But let's do something right away. Let's pop into the table, okay? Because we can verify a lot of this stuff using the table. In fact, let's go into our table setup really quickly. And why not start the table at -7 and make it go by ones? Okay, investigate this quadratic a little bit using tables instead of graphs. So we've got a table starting at -7 going by ones. So now let's take a look at our table. All right, nothing interesting at -7, but if we go down in the table, eventually we see at -2 we have at -3. I don't know why I've had this at -2 the whole time. My apologies. At -3, eesh. At -3, we've got a 0. All right. And there, take a look at that. At x equals 2, we have a value of -50. And at x equals 4, we have a 0 again. So my apologies, my sincere apologies at that -2. I looked at my graph incorrectly when I kind of glanced over at my answer key. But we can definitely see the zeros at -3 and at 4, and we can also see that extra point at 2, -50. The plain fact is, if we didn't account for the a, we would still have a 0 at -3 and at +4, but we wouldn't pass through the point 2, -50. So we're going to explore a little bit more about the a in just a moment. But pause the video now and write down anything you need to. All right, I'm going to clear out the text. Okay, we're going to still need that graphing calculator, so don't put it away yet. I will make sure it gets large when it needs to, but let's go on to the next problem. So let's investigate a, right? Because it's probably the most irritating part of this. But In exercise number 2, it says consider quadratic polynomials, quadratic, so x squared, of the form y equals a times x plus 2 times x minus 5, where, I don't want a to be 0, otherwise it's just y equals 0. Letter A asks, what are the x-intercepts of this parabola? I probably really should have said, what are the x-intercepts of parabolas that have this form, but I didn't. So anyway, think about that. What are the x-intercepts of this parabola? Right. They are -2 and +5. They have nothing to do with the a, right? Because if I, used the zero product law and I set this equal to 0, well, a can't be equal to 0. It's right here. So if this thing's equal to 0, we get x equals -2, and if this is equal to 0, we get x equals 5. Now, I had something get cut off here in letter B, but on your worksheet it probably looks correctly. It should say, sketch on the axes given the following equations. Let's just write that in, okay? So let's do this. Let's take our TI-84 plus, okay, let's make it large again, and let's put those 3 equations in. So let's go into y equals. Let's clear out our equation from the last one. And let's put in exactly like that. We don't have to multiply them out. The calculator doesn't care whether it's in factored form or standard form. So in y1, let's put in x plus 2 in parentheses times x minus 5, also in parentheses. Then in y2, let's put in 2 times x plus 2 in parentheses again times x minus 5 in parentheses again. Okay, I'm going to slow down a little bit, make sure you've got that all right. And then in y3, let's do one more. Let's put in 4 times x plus 2 in parentheses, and then times x minus 5 in parentheses. Again, kind of stepping back, right? We've got 3 quadratics that are really related. They all have the same factors except for the value of a. The first one, a is 1. We didn't write the 1, but a is 1. The second one, a is 2, and then the third one, a is 4. Now let's graph this thing, but let's make sure that our window matches what we have on those axes. So let's go into the window. For x min, let's put in -5. For x max, let's put in +9. For y min, let's put in -50. And for y max, let's put in +50. And again, let me pause just to make sure that you're keeping up. Make sure always that you're graphing these along with me. I mean, it's one thing to look at my graph, it's another thing to be going through the process yourself. So -5 to 9, -50 to 50. I think we're all set. Keep in mind that at least on my graphing calculator, when these graph, the first one's going to graph in blue, the second one is going to graph in red, and the third one is going to graph in black. All right, so that's the way I'm going to trace them out. I'm sure rather poorly, but let's hit the graph button. All right, it always takes a little bit for these to graph, but we're going to have them. All right. Okay, let's see if I can sketch them. As usual, it's always kind of a 1, 2, 3, 4, 5, always kind of a comedy of errors when I sketch them, but that's okay. So my first one kind of appears to be the sort of the widest one, but notice how it's going through the -2 and the +5. And then the one where a is 2 gets a little bit more steep and yet still goes through the -2 and the +5. Ooh. This could be a new low for me. And then the last one is the steepest of them all, again going through the -2 and the +5. All right. So at the end of the day, what we see is that because the x plus 2 and the x minus 5 are the same for all 3 graphs, they all have the same x-intercepts. And what A is doing, yet again from a previous unit, is that A is vertically stretching this thing. And if a had been negative, it would have also flipped it across the x-axis, right? So then the two tails of this x squared function would have been pointing down instead of up, right? So the factors dictate where we cross the x-axis, but the value of a then dictates how much the function gets stretched out from those fixed x-intercepts. It's like a parabola as a rubber band, and then you fix in the two x-intercepts and you're stretching from there. All right, so take a moment to copy down anything you need to, and then we'll clear out the text. All right, let's get rid of it. Now hopefully that gives you a better sense for why that a is needed in the factored form. Let's go on and work with some that are a little bit more challenging algebraically. All right, number 3, create the equation of the cubic in standard form. Man, this is important. I don't know about other states' tests, but on the New York State Regents, when they say it's got to be in standard form, it's got to be in standard form, and if it's not, they're going to take some serious credit off. But create the equation of the cubic in standard form that has x-intercepts of -4, 2, and 5, and passes through the point 6, 20. Then verify your answer by sketching the cubic graph on the axes below with the use of our calculator. All right, well, here's the thing. Right? We don't know what that a value is, but again, because we have a 0 of -4, we must have a factor of x plus 4. Because we have a 0 of x equals 2, we must have a factor of x minus 2. And because we have a 0 of x equals 5, we must have a factor of x minus 5. So that is sort of our first step, right? That is the equation of our cubic all factored out. What I don't have yet is that product worked all the way out, and I also don't know the value of a. Just like in exercise number 1, my personal belief is it's easiest to figure out a right now. That's my personal belief. So I'm gonna figure out a at this point. I'm gonna put 20 in for y, and I'm gonna put 6 in for x. So there, and there. All right, so just working this down. It's always pretty easy to solve for a. That's going to be 10. That's going to be 4. And that's going to be 1. Keep in mind that's all multiplication. Don't suddenly change it to addition or something weird like that. All of that ends up being 40. So in this case, a is fractional. A is 20 divided by 40, but of course, that's 1/2. All right, so this is going to get a little bit ugly because we have a fraction involved, but hey, this is Common Core Algebra 2, right? We should be able to deal with fractions, have confidence that you can do that. Now, to get it in standard form, this is where, we got to go back to some algebra that we were able to do in Common Core Algebra 1, but we have to be able to multiply that all out. I'll deal with the 1/2 later on. But the first thing I'm going to need to do is I'm going to need to find this product. Okay, I'm going to need to multiply all of this out. Now, we're multiplying 3 things, so that means you got to multiply 2, and then multiply by the third. Which 2 you multiply first is completely up to you. I'm not really sure why, but I always choose to multiply those 2 first. So x times x is x squared. Then we have -2x and -5x, which would be -7x, and then -2 times -5 is +10. That's just your standard foiling, right? Now I got to multiply a quadratic by a linear. So the first thing that I do is I multiply through by the x. That gives me x cubed minus 7x squared plus 10x. Then I'll multiply through by the 4x squared minus 28x plus 40. Now remember, I still have to take account of the 1/2. But I'm not going to do that until I kind of clean all of this up. So I'm going to get x cubed, -7x squared, +4x squared will be -3x squared, +10, -28 will be -18x, and then nothing really combines with the 40. So at this point, what I really have is this. Remember, that 1/2 is multiplying everything, not just the first term. So finally, I'll have y equals 1/2 x squared, oh, it's going to get ugly, minus 3/2 x squared, sorry, that's an x cubed. Go with the small eraser and make sure everyone knows it's a cubed. There we go. Sorry about that. Minus 9x, right? 1/2 times negative 18 plus 20. And that, is my final cubic in standard form. Now, what I'd like you to do at this point is put that into your graphing calculator, graph it, and do what we did in the last problem, not in the last problem, but in exercise 1. Verify that it's got those 3 x-intercepts and that it also passes through the point 6, 20. Okay, why don't you go ahead and do that now. All right. Well, I hope you did do it. In fact, 1, 2, 3, 4 kind of looks something like here. Here's -4. Here's +2. And here's +5. You end up getting a graph that looks something like this. Notice again, because it's a cubic, the ends point in opposite directions because the highest power is an odd power. And you can even verify that the point 6, 20 lies on that graph by going into the table like we did before. All right, nice cubic function. Obviously, this would get harder and harder the more x-intercepts we have, and the higher the power is. So an x to the 4th would even take more algebra, and x to the 5th even more algebra. All right, but we're going to stick with x cubes in this lesson. So pause the video now and write down anything you need to. All right, clear this out. Let's take a look at the last exercise. These are pretty long, so we don't have that many. Well, exercise 4 and 5. Let's take a look at exercise 4. It says, create the equation of a cubic in standard form that has a double zero at -2. We'll talk about that in a little bit. You've seen that term before, a double zero at -2, and another 0 at 4. The cubic has a y-intercept of 16. Sketch your cubic on the axes below to verify your result. Again, standard form. All right, well, let's start with factored form. Okay, it's a cubic. What does it mean for it to have a double zero? Well, what it means is that 2 of the factors have to be x plus 2. It's a cubic, so it's going to have 3 factors. So we'll have x plus 2 and x plus 2, and another 0 at 4. So that gives me my x minus 4. All right. Now, we need to figure out our value of a, and we have a y-intercept of 16, which means the point 0, 16 must lie on our function. Okay, well, let's put that in. Let's put 16 in for y and 0 in for x. Now, it's really critical that you have both of those x plus 2's. If we have only one of them, then we don't have a cubic, we have a quadratic. All right, this is 2, this is 2, and this is -4. And remember, these are all multiplying. 2 times 2 is 4, times -4 is -16. Whoops, I don't want that. I want my eraser. So we'll actually have 16 equals -16 times a. So that means a is -1. Right? A is -1. So now we're almost at a point where we can multiply it all out. All right, so here we are in factored form, right? This is my cubic in factored form, right? Some people would even write it like this, -1 times x plus 2 squared times x minus 4, right? So that double root is because our power is to the second. But let's multiply it all out. Again, for me, I will tend to multiply all this out first. So x times x is x squared, and then we got a 2x and a -4x, which is a -2x. 2 times -4 is -8. I start to do the algebra a little bit quicker as this course goes on because I assume that you want me to, that you can pretty much foil in your head at this point. So let's distribute the x. We'll have x times x squared, which is x cubed. X times negative 2x is negative 2x squared. X times negative 8 is negative 8x. 2 times x squared is 2x squared. 2 times negative 2x is negative 4x. 2 times negative 8 is negative 16. We're almost there. Nothing combines with the x cubed, but then we have negative 2x squared and positive 2x squared. Now that's kind of cool because these two just cancel. That's okay. We don't have to have every power represented. Negative 8x and negative 4x is negative 12x. And then nothing combines with the negative 16. We're almost there. We just need to multiply through by the negative 1. So we'll get y equals negative x cubed plus 12x plus 16. Good thing we had plus 16 there, right? Because we were told, plus 16, we were told we had a y-intercept of 16, so it's good that it turned out that way. All right. Now, what I'd like you to do is put that into your graphing calculator, graph it using the window given, and let's take a look at what that double root looks like. All right. You remember the double zeros from our work with the discriminant? That's exactly what's going on here. All right, and again, it kind of looks something like this. We've got our negative 2, our positive 4. This time, the ends point in the opposite direction, but in the opposite way that you'd expect. In other words, typically with a cubic, right, with a cubic, typically the ends point like this. But because the leading coefficient here is negative, they point in the opposite way. The left one is pointing up, the right one is pointing down. All right. And how would we describe the cubic at its double root in exercise 5? How would you describe that? Pause the video now. We had a nice piece of terminology for it. All right. So the cubic is tangent to the x-axis at its double root. Tangent, right? Just hitting the x-axis, but not cutting through it. And that should make some sense, because if it did cut through it, let me draw it in red. If it did cut through it, then the problem would be that there would be 3 distinctly different roots. Here we have 3 zeros, or 3 roots. It's just that 2 of them are the same, if that makes sense. All right, pause the video now and write down anything you need to. All right, let's clear out the text. Finish up the lesson. So, in today's lesson, what we saw was how a polynomial can be written in its factored form if we know what its zeros or its roots or its x-intercepts are, right? One little caveat, though, is that we have this leading coefficient of a, which can stretch the polynomial about the x-axis, so stretching it vertically, while pinning the x-intercepts, or the zeros. This value of a is almost always determined by some extra point thrown in. So here are your x-intercepts, and it's got to pass through the following point. All right. So I'd like to thank you for joining me for another Common Core Algebra 2 lesson by EE Math Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.